All right, let's dive right into this explainer and fundamentally unlearn everything we thought we knew about what makes a car move. We are stripping away the metal and the marketing to look at the raw physics of the electric vehicle powertrain.
Today, we are going to do a complete teardown of the electric vehicle. We'll be covering why there is no engine, the anatomy of the powertrain, stators, rotors, and magnets, the types of EV motors, why EVs beat gas, and finally, modeling the future.
Part 1. There is no engine. So you pop the hood of a modern EV, and you might just find a storage space, the frunk, right? Which begs a pretty massive question. Where on earth is the engine? For over a century, cars have housed these massive, vibrating blocks of metal right up front. But in an EV, that block is totally gone. Today, the thing doing the actual work is tucked right underneath you, integrated seamlessly into the bottom of the chassis. Instead of a complex metal box relying on thousands of literal explosive micro-detonations, pistons, and valves that generate crazy amounts of heat and friction, EVs use a surprisingly sleek, elegant system. There's no exhaust system, there's no fuel burning. We are talking pure electromagnetism propelling you forward. Moving on to Part 2, Anatomy of the Powertrain.
Let's trace the actual journey of the electricity here. It comes in through the charge port and sits in the massive traction battery pack as direct current, or DC. But here's the catch. The electric motor actually needs alternating current, or AC, to spin. That is exactly where the inverter steps in. It acts as this crucial translator, flipping that DC power into AC. Finally, that alternating current hits the electric traction motor and boom! It spins the wheels through a single-speed transmission. It is a brilliantly unified dance of components. The battery, the inverter, and the motor have to harmonize perfectly to translate stored electrical energy into physical momentum. Think of it like this. The motor's performance is completely capped by the quality of power the inverter gives it, which itself is totally limited by what the battery can actually push out. The whole thing is incredibly interconnected.
Okay, Part 3, Stators, Rotors, and Magnets. Now we're going to shrink down and travel right inside the motor itself. Let's start with the stationary part, the stator. The stator is essentially the immovable heart of the motor, manipulating electromagnetic forces without ever moving a single inch. Imagine an iron core wrapped in heavy coils of wire. When that inverter we just talked about feeds AC into these coils, it creates this incredibly powerful, invisible, rotating magnetic field. By just tweaking the frequency and magnitude of that current, the vehicle's computer perfectly controls your speed and torque.
And sitting right inside that stator, that's the rotor. This is the single moving part that creates all the torque you need to push a 2-ton vehicle down the highway. As the stator's magnetic field spins around it, the rotor, which is packed with magnets, is basically dragged along. It's constantly, desperately trying to catch up to that spinning magnetic field, and that rotational force is instantly transferred right to the drivetrain.
Which brings us to Part 4, Types of EV Motors. Now, not all motors are built the same way. The standard radial flux motor is super common and reliable. The magnetic flux shoots outward from the center, kind of like spokes on a bicycle wheel. It's really great for mass production. But then you have axial flux motors, like the ones from Yasa, and these are radically reshaping supercars. The magnetic flux travels parallel to the shaft. Amazingly, this allows for up to 4 times the torque density and literally cuts the motor's weight in half. That frees up a ton of valuable space for more battery cells.
We also have a big matchup when it comes to the rotor itself. We're essentially looking at highly efficient permanent magnet motors, which use rare earth metals going head-to-head against asynchronous induction motors. In an induction motor, there are no rare earth metals, but the rotor acts like it's always running just a tiny bit behind the magnetic field. Permanent magnets, absolutely brilliant for low-speed efficiency in city driving. Induction motors, they skip the expensive rare earth materials and give you massive high-power output, though they tend to be a bit heavier and less efficient at low speeds.
This whole thing directly highlights a massive, industry-wide tug-of-war, maximizing your driving range versus controlling raw material costs. As Tesla's chief motor designer pointed out when discussing the Model 3, permanent magnet machines often win out simply because they solve that cost minimization equation. They perfectly balance the motor cost, the battery cost, and the overall range. It's a constant game of optimization.
And just look at the hard data here. Companies like Yasa are hitting staggering power density numbers. Their prototype motor weighs an unbelievable 12.7 kilograms, but puts out over 1,000 horsepower. Meanwhile, brands like Lucid achieve over 97% peak efficiency with their radial designs. And look at Zeekr down at the bottom. They're actually using rare earth magnesium alloys for their motor housings to drop the weight by 22%, and they are hitting a screaming 22,000 RPMs without shaking the cabin apart.
All right, part 5, why EVs beat gas. So how does this electromagnetic marvel actually stack up against the century-old gas engine? The advantages are literally staggering. Electric motors can hit over 99% energy efficiency in some cases. Combustion engines, they waste massive amounts of energy as heat, maxing out at around 30% efficiency. Plus, you get instant torque right from 0 RPM. No gears to shift. Dramatically fewer moving parts means way less friction, heat, and maintenance. And regenerative braking is practically magic. You lift your foot, the motor reverses into a generator, and it captures that kinetic energy to recharge your battery while slowing you down. All with zero tailpipe emissions.
And if you want to get into the numbers, it's fascinating to see that permanent magnet brushless motors sit comfortably at an incredible 95.2% baseline efficiency. When you stack that data up against induction or switched reluctance motors, it becomes incredibly clear why the industry is leaning so heavily into permanent magnet setups for passenger cars. They just offer the absolute best output power to mass ratio.
Finally, part 6, modeling the future. How do we push these limits even further? Artificial intelligence. Using these modular frameworks, researchers can now mix and match data-driven machine learning models with hardcore physics simulations. So if an engineer wants to test a brand new battery chemistry, they don't have to build it physically first. They just plug the data models together virtually. The AI predicts exactly how the motor will react to the inverter's power delivery under all sorts of varying thermal conditions. This rapid virtual validation means automotive engineering is now evolving at the speed of software, leaving the slow, physical prototyping of the past totally in the dust. We are entering what researchers are calling the new automotive era. By using massively parallel cloud computing, engineers can run thousands of scenarios in the virtual world to find the absolute perfect balance of speed, efficiency, and range without ever turning a single wrench. When you combine motors that are already pushing past 95% efficiency with AI systems that can virtually iterate designs millions of times a day, the ceiling for this technology is basically non-existent. What you should take away from this explainer is that the shift to EVs isn't just about swapping out fuel. It is a fundamental, ground-up upgrade to the very physics of moving a vehicle. So with AI pushing electric motors to the absolute edge of what physics will allow, how long will it really be until the internal combustion engine is viewed as nothing more than an antique? Thanks for joining me on this deep dive.